Greetings, happy coders. Welcome back to Pacman, and this is the part 3. Hopefully this is going to be the last part. I think 3 parts is more than enough. And today we're going to be looking at a few different things to finish off the hack to show you what else I did. So I'm going to start the game here. Let's unpause it. Okay, so we got to the point in the previous video where we have drawn the map successfully with new graphics, and we've put the ghosts in the right place. So the next thing that we want to think about is how we can fix these sides, because obviously in the original the exits were here and here right at the end, and now they're a little bit more to the center. So in a situation like this, you always use what you already know. So some of the things we already know are, we know that the coordinates of all these sprites are held in row and column values. So that means if we're looking for an exit, it's going to be a column value rather than a row. And also it's going to be a value from 0 to 31 rather than a pixel value of 0 to 255. So what we're basically looking for then is some kind of a check for an address here, which would be coordinate 0. So let's say, for example, this ghost, if the ghost's position is at 0 or perhaps at 31, then it's going to be changed. So I figured that 0 is an acceptable coordinate here, but if it goes off 0, then obviously in 8-bit numbers, if you go from 0 and you subtract 1, it basically just loops itself around and goes to 255. So for that reason, I'm going to be looking in the code for some kind of a compare with the number 255. Now obviously there's probably going to be a few of these, but we know roughly where to look, because obviously it won't be in the ROM, it won't be in the screen memory, but it will be just after that. So there's a certain fixed area that we can look in to check for that, and when we find one of those, we'll look to see where that value is coming from, and that will give us a clue as to whether it's the ghost address, because we know that the ghost addresses are held at approximately address 6F00 onwards. So we'll be able to look for a check for something similar to that. So here is the debugger. And what is a debugger, you may well ask? Well, basically this is a little sort of application that's built in that allows you to track and trace the code as it's running, and you can therefore look at the registers here and see what's happening, see what's being changed. Fuse, obviously we used the debugger in Fuse as well, but this one is it's not as powerful as Fuse, but it is a little more user friendly because I can use it to sort of scan through the memory using the mouse, and I can see all the registers easily, and I can also change them. So what are we looking for here? Well, essentially, let's take a look here, for example. Look at this point here where it's roughly where I've frozen the code, but I'm going to pick out this point here, because what we've got here is compare to 255. Now what I want to do then is I want to look through the code to find any examples of this compare 255, and we can see that the hex equivalent of compare 255 is FEFF. Now this one is loading in at 68B8 and comparing to FF. So 68B8 is not where the ghost data is stored. So although this one might be used, for example, for the Pacman, right now we're not going to look at that one too closely. Instead, I'm going to do a find, and I'm going to look for any other FEFFs that I can find. So just to be clear on this, what I'm doing is I'm looking for these two numbers next to each other in the memory, because these two numbers next to each other could correspond to a compare to 255. So if you imagine in BASIC, all the commands that you use in BASIC, such as print or input or go to, each one has a token, so each one has its own number, and that's how it's stored in the memory. And this is a very similar principle here, because you can see there are various commands here, such as call or compare or load, and each of them has its own code here. So for example, if you look at this here call, you'll see that you've got CC here. This is call Z, and here are there's a couple of others which is just call, and you can see CD is call here and CC is call Z. You see there's another call Z there, CC, and these two here, 786C, those are the numbers there that's telling it what it's going to call at that point. So each of these down this row here corresponds to a command. So FEC8 would mean compare to C8, and FEFF, as we mentioned, means compare to FF. So we're looking for compare to FF, which is 255. So let's take a look at a few of these. Now this one, if we look a little bit higher up, what we can see here is 67F3, and actually we know already that this is one of the location in memory where the first red ghost is actually stored, and it looks to me like this is a kind of a loop which is going around and checking each of the ghosts. And in fact, if you look here, we've also got a compare to 1F. Now 1F is 31, so that tells me that this is comparing the position of the ghost to 255 and 31, which it's jumping to the same place. This is a jump, and it's jumping to the same place if it has a match. So this Z here means if it's equal to, essentially. So if you're curious, what actually happens is the value is in the accumulator, so it's then compared to the value that you specify, and this value is subtracted from one from the other. And so if you get a value of 0 from that, it means that the two are equal, because for example 5 minus 5 would be 0, and that's the way that Z80 calculates an equals to. It does a subtract, and if the result is 0, it means that it's equal. But of course it doesn't actually change the accumulator, it just does the test. So in this case we know that the accumulator would be 0 if this compare happened. So a compare command is basically like saying to the computer, what would happen if I subtracted this number from the accumulator? And so in this case we're saying, what would happen if we subtracted 255? Would the result be 0? In other words, would it be equal? And if it is, then jump to this number here. So what we can do is we can click on here and see where it goes. And what I can see is it's making some additional comparisons here to other numbers which are outside of the range of the column. So I'm not going to worry about that. But what I do see is a jump here to 6BA7, which goes to here, decreasing, and then it's comparing it to FF here, which is 255, and then it's loading it with 1E here. In other words, if you are at 255, then, and as you can see here, jump if not 0, so this is a not equals. If it's not equal to 255, then just continue, but if it is 255, then reset it here to 1E. So this is the point at which the ghost is going to be reset to 1E here. And what I can see a little bit further down here is we've got compared to here 31, and if it is 31, if it's not 31, just continue, but if it is, then set it at 0. So in other words, this is doing the same thing, but it's doing it at this end here. And so this point here is where the ghosts are reset to 0 if they go out of the maze. And this point here is the point at which the ghosts are reset to, in this case, 30, when they go from the other side of the maze and out again like that. So that's pretty much how that works. So all we need to do is change these numbers so that instead of comparing to 1F, we'd need to compare to something like, well, so 1f is 31, so it's something like 31 minus 6, so I guess maybe 25, and then on the other side we'll do plus 5, something like that, plus 6 maybe. So with a little bit more searching, we could find the rest of these as well, if there are, for example, for Pacman and for the eyes. And in fact, if I do a search for this, you see here 0E, 1E, which is load C with 1E, that would be a good place to look, because we now know what the routine is doing. And we can look for something similar to that in the code. And here we can see, let's see what we found here. Yeah, something very similar here. Load CA, compare FF, here compare with 1F, and here reset. And here reset to 0. So again, this is very likely to be what happens when Pacman maybe goes out, because we can see it using IX, so IX could well be the Pacman sprite. And again, there's a certain amount of guesswork here, and what you normally do is just do a bit of poking and around and see what happens. But what I'll do is I'll put a break in here and we'll see what happens to these 2 points here. So what that means is that when this value is set, so I won't put this compare, I'll put it where it loads it here. Yeah, so this one loads it with 1F, this one loads it with 0, 0. So let's put a break in here and see what happens. And there you go. So what you can see here is immediately it's loading with this value 1E, so it's resetting here. So, and within Spectaculator, I can edit this directly. So instead of 1E, let's put in, say, 9, like that, here. And down here, we know that this one is probably the other way around. So we'll put this one in as, say, 5, like that. Let's see what happens now if we continue. So what you could see there, I hope, it was very quick, but basically Pacman, instead of appearing here, appeared here. Now this jump has come in again, and in this case you can see it's now going to load it with the value 5, which means he should, if this works, and we're pretty sure it does, should appear somewhere around here. 0, 1, 2, 3, 4, 5. So he's actually one out. Probably should be 6. So let's change it to 6, like that. Okay, let's continue. There. So what you can see now is that we've managed to fix the setting. I'll just do it one more time just to show you here. Okay, and now we've crashed the game, and the reason we've crashed it is simply because the ghosts, I don't know if you noticed down here, but they went off for a wander, got completely lost and disappeared off the edge of the screen. But anyway, I'll leave that in because it is quite funny. But essentially we found the thing that we're looking for, and we can reload the code back in, and we've still got the trace active. So it's a pretty straightforward thing now. What we've managed to do is we've managed to reset the maze left and right, but at this point we're still doing the same check for the edges, so we need to change those as well. So I worked through the code, looked for those patterns, and managed to find all of them for the ghosts, for the Pacman, and also for the eyes as they're returning to the maze. And I'll show you those now. So I've gone back to our Excel spreadsheet, and which you may remember from the first video where we were working out the ghost positions, previous video, and I've now put in some extra code here with various values. These are the addresses that need to be changed. These ones here, and all of these. So there are 3 for the left, 3 for the right for the ghosts, same for Pacman here, and the same for the returning eyes as they return to the center of the maze. Okay, so that's quite a lot of pokes to put in manually, so I'll show you something that I do sometimes, which is also quite helpful. So this is a text file, and it's something called a POC file, P-O-K, and it was used originally with things like multiface to allow you to poke memory to sort of hack games and put in infinite lives and various things like that. And it's a text file, and it's compatible with Spectaculator and Fuse and probably a few other emulators, and it therefore gives you the possibility to create a list of pokes that you want to change. Now, if you want to Google POK ZX Spectrum format, I think you can find something on World of Spectrum. It'll give you a bit more information about how to do this. But yeah, you can basically make a list of pokes like this, and the advantage of this, of course, is aside from doing it manually, which of course you could do, you can use OpenOffice. So if you take a look here, you'll see I've made a sort of macro here. Well, it's just a function basically. So concatenate m space 8 with a hexadecimal conversion for this address here, D15, and then a space followed by this one, which is the new one, and a space followed by the old one there, and that creates this entry M827434555. I create a list of these. As you can see, there's another one there. Just cancel that, and all I have to do then is do the same thing for all of these, for this, this, and this, all of those, and then put them together, and then for the very last poke I'll just change the M here to a Z, and I'll create a POC file. And you can see, we'll go back to that POC file there, you'll see 274345255, as you'll see in the POC file, which I have here. Exactly the same thing, 27434, and the rest of them. And this is all in decimal, of course. So once this file has been created, I save it off, and I can then load it into Spectaculator. Here it is, and we'll try now to load in this maze exits poke, and it comes in, it says Pacman exits. You click it, press OK, and all of those pokes that I've defined will now be applied. So let's try it out. Okay, so I've still got the debugger on, so I'll turn it off. As you can see, that's quite enough of that noise, isn't it? But as you can see, the maze exits are now working perfectly. So what else is there to do now? Well, the rest of it should be fairly simple and straightforward to do. This is definitely the trickiest part. We need to find something that's counting the dots. We need to find where the dots are flashing. These ones are flashing. And we need to change the font here as well. So let's get to work on that now. Okay, so here we are back in Fuse, and the game is about to start. And for most of the stuff that we're going to do now, we're just going to use the debugger to try to figure a few things out. So the first thing I want to do is figure out how the dots are counted. I'm going to work on the basis, and it is an assumption, but that the count's going to start from 0, and when it has counted all the dots, it will then reset to the next level. That's probably the most likely way that it's done. It could be a countdown. But I'll look for a countdown if I don't find a count up. So right now we've got the poke finder open, and we're going to search for the value 0, and obviously there's a lot of zeros, but that just sets us off for the rest of the poke search. Now what I'm going to do is, we're going to see here that Pacman's going to start eating automatically here, and he's going to eat 1, 2, 3, 4, 5. So the next thing that I'm going to look for is 5. I'm not going to do it yet. I'm going to do it once we've unpaused the game. Okay. And as you can see, there are only 2 values that changed from 0 to 5 at this point. So we can be almost certain that one of these is the dot count. Now why are there 2 values, you may well ask? Well, the main suspect here would be this. As you can see, the score is also 5. So and of course the score is going up here, not in tens but in ones, as we mentioned. So the issue we have is that the Pacman count is going to be equivalent to the score. What can we do about that? Well, the easiest thing to do would be to eat this power pill, because that will count as a dot, but it will also give a different score. So rather than 5, we'll go 6, 7, 8, 9, 10, 11, 12. So this time in the poke finder, we'll put 12 in here, ready to go. We don't press search yet until we're ready. We'll press unpause. Okay, so let's try to look for 12 now. So as you can see there, we've got 281B, which has come up as our final value here, 281B. So we need to add on, obviously, the offset here for the page, which will add 4000, 16384 to that. We'll do a quick calculation. So 281B here is 10267, and we'll add, which gives us a total of 26651, or 681B in hex. So the next thing that we're going to do is we'll go to the debugger, and we will put a break in as we did before. So this time we'll say break when writing to 681B. We need to put that as a hex value, of course. There we go. So what this will do now is it will basically give us a breakpoint when the number of dots increases or has been changed. So let's unpause the game. Nothing happens, but as you can see, I just moved up to eat a dot there. And let's take a look at the top of the list here, and we can see what's happening. And here is 681B. I'll explain to you what's happening. It loads the value of the number of dots in here, increases it, compares it to this number, EC, and if this number has not been exceeded, it makes a jump. So therefore, we can conclude that this number here is the dot count. And so let's see what that would be in hexadecimal. So rather decimal. So EC dot count 236. Okay, so what I'll do now is I'll poke that value here. So the value here is 6ECC. So that would be, as you remember, the code would be FE and then EC, because compare is FE. So the number here would be at 6ECD. So we need to poke 6ECD. Let's take a look at that in here. 6ECD. Let's bring that across. Okay, so decimal 28365. So we'll close the debugger and we'll take away the breakpoint, like so. I think that might be our last life, so okay. So let's put in a poke to memory, 28365, and we'll poke it with, say, let's poke it with 5, because if we do that, then the level should finish after 5 dots have been eaten. So let's see what happens. There you go. So that's our magic number. And as you can see, so there you can see we're skipping through the levels because we only have to eat 5 dots to go to the next level. So this address here, 28365, is the poke that we need. So now we just need to count the number of dots that we actually have in our new maze. So we're back in AGD here, and this is the new maze, and I've added an option within AGD so that to the source code to press a key, and it will tell me, as well as the addresses that I need to write to, it now also counts the number of dots here. And what it does is it counts basically every time when it's drawing this, it counts all these dots and the power pills to give me a total of 158. So basically 158 is the count that we need to change. So all we'd have to do then is the poke that we need is 28365,158. So we'll remove this one. We'll add the new one like that. And I will now proceed to try to complete the level. And I'm now back. I've just skipped the video there, and I'm just at the point here where I'm about to finish the level, and let's see what happens. There you go. So you can see 158 now works. Okay, so what remains to be done? First of all, we need to think about these flashing dots, and we also need to think about the font. Now, in terms of the flashing dots, originally they were over here. Now we know that this part of the panel here is actually the same ink as this part. So it means that these dots are not being drawn using pixels, because we would see them if they were. What it tells us is that it's actually being drawn using attributes. So in order to do this, I went back to the original game and looked for the screen attributes that were here, here, and here for the dots when those were being written to, using the debugger in the same method. I found those addresses and I changed them to the correct addresses here for the locations of the power pills. And as a result, that basically enabled them to be turned off and on. So that's how that was done. And obviously it's not done using Flash, because otherwise the other sides would be there. It's done by printing attribute 0 and then replacing it with the yellow one. So basically the pills are always there, you just can't see them because they're hidden by the attribute. And so that was quite an easy fix. So the last thing we wanted to do then was look at changing the font. And again, this was fairly straightforward, because we know that whenever anything is being printed, it's going to choose either the font, which is the one that we've got here, used, all the kind of mixed graphics here, user-defined graphics, or it's using the ROM font. And so there'll be at some point in the code where it switches from the, let's say, the Pacman set of characters to the ROM font. What we want to do is change it so that instead of switching to the ROM, it's going to switch to our new character set. So here we are once more in AGD. This is the font editor, and this is a standard classic arcade font as used by Nintendo, Namco, and so on. And we won't need this last line here. We'll only need the font for the writing here, and for this section here with the score, question mark, exclamation, so on. So we only need 500 bytes. So all we would do here then is save off a binary and save it off as 512 bytes starting from address 31232. And in terms of where we load it, we know that the original character set, the one with the Pacman graphics, that one is stored at 32,000. So we need to basically think about 768 bytes after that would be 32768. So we can load the data in at 32768 because we know that the top part of memory is not used because this is a 16K game. So therefore we'll save the file off here. So we'll call it 32768 new font dot bin. We'll save it off at 31232, and it's 512 bytes in total. Now, could actually, if we really needed to save memory, we probably wouldn't need these characters either. In fact, quite how many of these are even used is debatable. But we've got plenty of space, so we'll keep it nice and simple. 512 bytes from here to here. So that file's done. Now we just load it into the game. So here we are back in Fuse with the game, just finished. and I will now load the binary into here. See, it's here 32768, and we'll load it in 32768 like that. Okay, so we're back in Spectaculator, and let's talk about this font. Now, as mentioned in a previous video, the location for the font currently in use by the ROM character routine is held at addresses 23606, 23607. Now, quite often these fonts are stored in sets of 512 or 768 bytes, and they're byte aligned, which means that the low byte is usually 00. So normally, rather than look at 23606, we normally look at 23607 to locate the font. So let's take a look at the ROM. Okay, so I've gone to a website here, schoolkid.github.io, which basically allows us to see where things are stored in the Spectrum ROM. And we can see the location of the character set here at 3D00. Now this is the start point at which character 32, which is a space, begins. So if we need to point at this, we need to go back 256 bytes, because the first 32 characters are control characters. So the address will be 3C00. In other words, the value held at 23607 will be 3C when the ROM font is in use. And that means that when the game switches to print the high score table, for example, then it will be loading the value 23607 with this address, with this value here, 3C, not 3D. So we're going to look for that, and then what we'll do is change it from 3C to the value that we need. So we're loading the font in at 32768, which would be here, and so the number would be 80. We don't need to worry about this. However, we do need to drop it back by 1, as we saw here, so the value will be 7F. So we're looking for something at 3C that's loaded at 23607, and we're going to replace it with 7F here. So let's go to Spectaculator and start looking at how we do that. So I'm here in Spectaculator, I'm going to the debugger, bring that across, and I'm going to find these two values, 3E, 3C. Now we know we're looking for 3E. 3E is a command. Let's find out what command it is. And here's an example. And you can see here we've got load A 3C and then load 5C37 with A. Now what hex value do you suppose 5C37 is? Well, here it is in the calculator, and as you can see here, it's 23607. So we found a point in the code here which is loading the value 3C into here. So the next thing that we need to do is point it instead at 7F, which is where we've loaded the binary. Okay, so we'll just go and directly edit this here, and we'll change this to 7F. See if there are any more. So again, 5C37, that's a good sign. There's another one here. So this is the game switching back and forth sometimes between the two different sets. So it happens on a number of different occasions, as you can see. But basically, we just need to change all of these. As you can always see that it's loading it in there straight after. And then there's this one here, which difficult to say what happens here because it's making a jump. And it's jumping down to here, and it doesn't seem to be loading into the correct place. So we'll leave that one and just see what happens. I think that's the only one that's, yeah, the rest of them are going to be in the ROM, so don't need to worry about those. So we'll now go back into the game and see what difference that has made to how things are working. Okay, we'll let the game switch over. Of course, right now it hasn't made any changes, so what we might need to do is start the game and then exit the game. There you go. Okay, sorry, it's a little bit loud. You can see straight away that it's already had an impact here. We've already changed this font, so it's just a question of now seeing what happens when the game resets back to its state when the game is over. So I'll let the game finish and reload back in a second. And as you can see, we've now got the font working correctly in the game here, and the high score and everything else is all correct, and when you go into the game, as we already saw, that also works. Okay, so that's basically it. Now we've done all of the things that we set out to do, and all that remains then is to think about some possible additions that we might do. You may have seen that for my Patreon members I created some arcade artwork here and here, and it's also possible, for example, if you really wanted to do that, you could look at adding additional mazes and various things, which I have considered, but I've decided that I am going to go and work on my own version of this with a smoother Pacman, because as much as we've improved all of this, there's no denying that it's still quite a jerky game. It doesn't really feel like the arcade, even though it looks like it. Probably one of the better versions of Pacman for the Spectrum now, I would say, but I think I have a few ideas about a few things that could be done to make it nicer than this, and but if I am going to do that, I think I'd rather start from scratch and make my own title. So that will be another video at some point in the future. In the meantime, I hope that you've enjoyed this. It's been quite a slog, but I've enjoyed it too. And if you'd like to see more of these kind of videos where we take a particular game, take a deeper dive into the code, make some changes and do some hacking, then I'd be happy to do that, so let me know. Alright, in the meantime, take care, stay safe, and happy coding. Bye-bye. This video would not be possible without the amazing contributions from the people whose names you can see scrolling up the screen right now. If you'd like to be one of them, you can get all my games for free, you can get some coding tips, you can even get to dictate which games I work on in the future, and you might even feature in them. So if that sounds good to you, then head over to the Patreon page. The link is just coming up now. And in the meantime, happy coding. Bye bye.